Have you ever wondered how these metallic kitchen items are made? This steel container or this metallic sink, for example, or how these complex and nicely curved car bodies, auto bodies are manufactured, or the fuel tanks are manufactured, or even beverage cans. If you look closely, you will notice these shapes has no joints or welding on their entire surface. These all are made from a single sheet of metals, formed into one seamless piece. Now you might thinking these parts are made using casting process, perhaps die casting, but this is not true. If they were made by casting, they would be much more expensive, and achieving such high quality surface finishing would be difficult. So the process used to shape sheet metal piece into these smooth and complex 3D form is not magic, but it's called drawing process. Yes, you heard that right, the drawing process. But this has nothing to do with sketching or painting. The term drawing here comes from the word drawn, which refers to pulling or stretching a metal into a die to form the desired shape. And when the depth of the final shape is greater than its diameter, then we call this process deep drawing. And this video is all about deep drawing process. End of this lesson, you will know everything that a mechanical engineer must know in order to design the die and the punch for a deep drawing parts. Like how to calculate the minimum radius of the punch and die, how to determine the correct clearance between die and punch to ensure there is no wrinkles or defect in the final parts. Also, how to calculate the blank size, the size of the flat sheet before drawing. Also, the understanding of drawing limit of sheet metal. And most importantly, how to calculate the amount of force required to draw the sheet into die. Because this calculation is crucial for designing the press machine, typically a hydraulic press, for deep drawing the part. So let's first deeply understand the drawing process. So drawing is a manufacturing process that uses tensile force to elongate materials like metal, glass, or plastic. As the material drawn or pulled, it stretches and becomes thinner and taking into desired shape and thickness. In simple terms, in drawing, we apply tensile force. Tensile force means pulling force, which creates tension in material, which is opposite of compression. And this is the key difference between drawing and rolling. In rolling, the material is compressed between rollers, but in drawing, the material is pulled, caused to stretch, undergo plastic deformation, and become thinner to achieve desired shape and thickness. If you started thinking that drawing is related to only wire pulling, so this is not the case. Drawing process is broadly classified into two types. One is wire bar and tube drawing, and one is sheet metal drawing. So let's understand one by one. So in wire drawing, a wire is pulled through the die to reduce its diameter while improving its mechanical properties like strength, surface finish, and ductility. Common application includes making electrical conductors, cables, springs, fastener, and structural reinforcements. Wire drawing is typically performed at room temperature, making it a cold working process. However, for a large wire or tube, it can be performed at elevated temperature as a hot working process to reduce the required force to pull the wire. Wire drawing dies are typically made of tool steel, tungsten carbide, or diamond. Tungsten carbide dies are used for steel wire drawing. Cast steel dies are used for hot drawing. And diamond dies, single crystal diamond dies, are used for drawing a very fine wire. And these dies are mounted in a steel casing for supports and easy replacement. Die angles are typically from 6 to 15 degree with at least two angles in dies, the entering angle and the approach angle. Now the sheet metal drawing. So in sheet metal drawing, the sheet is not pulled along the thickness of the sheet. Instead, it's plastically deformed to achieve the desired 3D shape. Simply, this process involving shaping a flat sheet into form a cylindrical, hollow cylindrical shape or hemispherical shape or any other complex counterword shapes using the die and punch. And the process is classified as deep drawing when the depth of the part is exceed its diameter. The too much depth is typically achieved by redrawing the parts through the series of dies to gradually form the desired geometry. Now, when the sheet is pulled into the die, the flange region, the sheet metal around the die shoulder, experience two types of stress. One is radial drawing stress. This is a stress directed towards the center as the material is pulled into the die, and one is tangential compressive stress. This stress acts along the circumference of the die shoulder, also called as hoop stress, due to material retention. And these compressive stress can lead to wrinkles formed in flange area, which appears as uneven deformations. So to prevent the wrinkles, a blank holder is used in addition to die and punch. This ensures controlled material flow in die during the drawing process and prevent excessive compression and wrinkles formation in the flange area. For application requiring complex counterword shapes with a smooth transition, the conventional die and punch method may not be suitable. In such cases, unconventional deep drawing methods are used. First is hydroforming. In this process, instead of using metallic punch, we use hydraulic pressure to draw the part into the die. But for this to work, we need to seal the cavity with extremely high force. Make sure the high pressure oil doesn't leak. Hydroforming gives us freedom to form complex curvy shapes that are almost impossible to achieve with conventional method. And this is why this method is widely used in automobile industries to making like body panel, the chassis component or the fuel tank of the car. Next is rubber and pad forming. Here the sheet metal is pressed between the die and the rubber blocks, usually made of polyurethane. Under high pressure, the rubber pushes the sheet into the die and forms the required shape. Just like hydroforming, this method allows the sheet to form in two directions, which is not possible with a standard die and punch. And don't think that the rubber pad is only used for light pressing. You will be surprised. There are massive rubber pads pressed in Netherlands, including one that delivers the pressing force of 8,000 tons with working area of 1.1 into 2.2 meters. And now let's talk about the future, the digital deep drawing process. This process is fully programmable, meaning we can use the 3D CAD model to turn a flat sheet into any shape with incredible accuracy. While it's still a relatively new technology and very expensive, making it a game changer for custom design and next generation manufacturing. So this was all about the methods of deep drawing. And now it's time to understand the critical parameters related to deep drawing process. that we need to know to design the punch and die for the deep drawn parts like die radius, punch radius, die clearance, blank size, LDR limit, or even calculating the required force for drawing process. So to make this practical, let's say we are designing a stainless steel simple cup, a container by deep drawing process. So this is the required size of the cup. The inner diameter is 160 mm, depth is 60 mm, and flange is approximately 20 mm, and the seat thickness is, let's say, 1.2 mm. So our first step should be blank size calculation, because this will determine the other parameters as well. So since we are making a cylindrical container, the blank shape will be circular, right? And the total volume of the blank material will remain the same after the deep drawing process. In simple terms, the surface area of the container will be same as the area of blank. So let me first create a rough model of this container in SolidWorks. I have used revolved command to model this container, and this is not the final design. We will have to refine this design after calculating the other parameters like radius of the punch and die. For now, it's just for estimate the blank size. So we can use geometrical formulas to calculate the area of these surfaces, or better yet, measuring it directly in CAD. So the area of this entire sheet is 61575.22 mm square. And since the blank is circular, we can use the formula of the area of the circle. So put the values, and R will be 140 mm. So the diameter of the blank will be 2 into R, 280 mm. Now, before calculating any parameters, let's first determine that if we can achieve this shape in a single stage of drawing, or we need multiple stages of drawing. Why? Because sheet metal has a limit of drawing. If we will try to draw more than its material can handle, the sheet metal will be cracked. And this limit is represented by the limiting drawing ratio, LDR. The first draw reduction is typically limited to 45% for mild steel, for MS, and up to 50% for materials like brass or bronze. This means an MS sheet can be safely drawn in a cup with diameter 55% of its blank diameter in the first draw. And anything beyond will require multiple drawing stage. So to check the limit, we can use reduction percentage formula, where D, the capital D, is blank diameter before drawing, and small d, small letter d, is the desired cup diameter. And here's the critical part. The flange of the cup doesn't get drawn into the die during the process. So we calculate the blank diameter for the cup by excluding the flange from the total blank diameter, because this is not going to be drawn, so it should not affect the drawing capacity, the drawing limit. So the blank diameter with flange is 280 mm and the flange radius is 20 mm. So the cup diameter which is to be drawn will become diameter with flange minus 2 into flange radius. So it will become 240 mm. And now let's calculate the reduction percentage. So it will be 240 minus 160, the desired diameter 160, divided by 240 into 100. So it will be 33.3%. So since the reduction percentage is 33.3%, which is less than 45%, means we can safely achieve this shape in a single stage of drawing operation. Now let's move to calculating the die radius. So for the smooth material flow, the die edge must have a generous radius, ideally 4 to 6 times the sheet metal thickness, but never should be less than 3 times of the sheet thickness, because a smaller radius hinders material flow into the die. which leads to tear and cracks. And larger radii reduce the pressure area between the blank and the blank holder, which can cause wrinkles near the die edges. So to prevent these wrinkles, we keep extra blank material for proper gripping, which will be trimmed after the drawing. However, the die radius should not exceed 20 times the sheet thickness. And this is the formula for optimum die radius, where D, the capital D, is blank diameter of the cup, small d is the cup diameter after drawing, and T is the sheet thickness. So put the values and it would be 7.8 mm. So we can round it to 8 mm for simplicity. And now let's move to the punch edge radius. So as per thumb rule, the punch radius should be more than the 3 times of the sheet thickness, but should be less than the 1/4 of the cup diameter. Why these limits? So the excessive punch radius reduces the contact between the blank or the cushion, leading to the pokers at the bottom. And too much sharp edge can damage the sheet during the drawing. So our punch radius should be between 3.6 to 40 mm. So let's consider 8 mm, matching to the die radius for symmetric and better aesthetics. And now the next critical parameter is die clearance. The gap between the die and the punch and the space for the drawing is intentionally kept larger than the sheet thickness by 7 to 15%. And this additional gap is referred as die clearance. And this is crucial because it's reduced the friction between the die sides and the workpiece. It's allow for smooth material flow during the drawing process. And we can refer to a standard table for clearance for drawing dies. For blank thickness 1.2, it's 1.25 mm. We select the clearance of 0.1 T for the first draw. So the clearance should be 0.1 into T, 0.12 mm per side. Now let's adjust the dimension of the punch and die based on this clearance. So the punch diameter will reduce by twice of the clearance. So it will be 159.76 mm. And the die diameter is increased by the twice of the sheet thickness plus the twice of the die clearance, 164.8 mm. Now, just for side note, this calculation assume mild steel for shear strength 40 kgf per mm square. For other material, the clearance can be estimated using this material specific formula. Since SS304 has approximately the same shear strength as mild steel, so we will not consider this additional adjustment for this case. So for now, we have almost all the parameters related to die and punch design. But how much force will be required to draw this sheet, this blank sheet, into this final shape? So to calculate the drawing force for a circular cup, we use this formula, where this small d is the diameter of the cup after drawing, capital D is the diameter of the cup blank size, and T is the sheet thickness, and sigma is the yield strength of the material. So for SS304, it would be around 250 Newton per mm square. So put the values and it would be 135648 Newton. Now, this force is required to draw the part into the shape, but we will also have to consider the frictional resistance during the drawing. So to estimate the press capacity, we should consider around 40% more than the drawing force. So the press capacity should be 189907 Newton. In kgf, we can divide by 9.81, so it would be 19358 kgf. And into ton, it is 19.3 ton approximately. So let's round it to, so we need 20 ton capacity press. the hydraulic press that we will use to drown this blank sheet into this cylindrical nice cuff container. So in next video we will use these parameters to design the die and punch tooling for this drawing process. But remember, the designing a punch and dies is not as simple as it looks. There are numbers of practical considerations that we have to consider during designing the tooling, drawing tool or any other tool. So get ready for design with me in next video. Next video should be on the screen, or you can check the video description. And thank you so much for watching this video.